Thus, you can run that video.
Of Structural Engineers, also known as IS Struct E, was conceptualized and constituted in the year 2002 by a group of senior professional structural engineers from all over the country. IS Struct E is registered under the Societies Registration Act 21 of 1860. IS Struct E is a national apex body of structural engineers in India with a mission to promote structural engineering profession and cater to the professional needs of the structural fraternity. In the short span of 2 decades, association has attained an eminent position in the professional field. Its membership is valued very highly in the profession. Since inception, IAS Struct E has been led by eminent structural engineers like late Shri Mahendra Raj, late Shri Shri Kumar Ghosh, Shri Subhash Chand Mehrotra, Professor Mahesh Tandon, Shri Alok Bhaumik and Shri Manoj Mittal as its president. IAS Struct E is a permanent member of Engineering Council of India and interacts with the government on professional and policy matters related to civil and structural engineers. To expand its reach, IAS Struct E has collaboration with various international professional like-minded associations and institutions. IAS Struct E's prime objective is supporting and protecting the profession of structural engineering by upholding professional standards and acting as a mouthpiece for structural engineers in India. IAS Struct E endeavor to ensure that its members develop the necessary skill in structural engineering and work to the highest standards by maintaining a commitment to professional ethics and standards. IAS Struct E is actively engaged in organizing several continuing professional development (CPD) courses for structural engineers to help them update their knowledge and advance their career paths. It also conducts refresher courses for young and practicing engineers and student-oriented programs. Seminars, workshops, conferences, technical lectures and discussions related to the latest technological advancements and case studies are also organized regularly for members to enable them to continuously update their knowledge and skill set by interacting with the best minds from the industry. IAS Struct E's activities are widely appreciated and known for quality technical contents. IAS Struct E is also actively engaged in publishing its quarterly journal Structural Engineering Digest (SED), code commentaries, professional guidelines and a monthly newsletter. IAS Struct E's publications are becoming popular with time. IAS Struct E has representation in various technical committees of BIS and IRC as well. Its members are actively contributing to National Code of Formulations. In the year 2020, IAS Struct E started National Awards competition to stimulate interest in the structural engineering field and to promote innovative thinking and creativity. The awards are presented to the winners in recognition of their outstanding contribution to structural engineering in the categories which include Outstanding Structure, Outstanding Structural Engineer, Outstanding Woman Structural Engineer, Promising Young Structural Engineer, and Best Master's Thesis in Structural Engineering. IAS Struct E is currently operating from 4 regional centers, namely Eastern, Western, Northern, and Southern, having its headquarters in Delhi, to inculcate the professional culture and provide handholding to the budding engineers. IAS Struct E has its student chapters in several leading engineering institutions as well. Membership of IAS Struct E is open to all civil and structural engineers engaged in structural engineering profession. Members are elected based on their qualifications and experience in different grades as per eligibility requirements prescribed in the bylaws. Each application is carefully scrutinized before electing the members. More information about IAS Struct E is available on its website www.iastruct.co.in.
I think Dr. Dhawan, would you like to start?
Hello.
Yes, you are audible.
Okay. Welcome to to attend this webinar. The topic is roadmap to carbon neutrality in the built environment for India. I'm glad to introduce our moderator, Mr. Alok Bhumik, who is now the managing director of B&S Engineering Consultants Private Limited. He was the past president of Indian Association of Structural Engineers. He is well experienced, and most of us know him. So I will not say further. He is one of the outstanding consultant dealing with long span bridges. I hand over further to Mr. Bhumik to introduce the topic and the speaker.
Thank you. Thank you, Dr. Dhawan, for this brief introduction. Hello, everybody. Good morning, good afternoon, and good evening to all. This is a very important topic on which we are having this webinar. The topic roadmap to carbon neutrality in built environment in India. This is extremely relevant to the society at large. First of all, there may be many uninitiated in the participants. So let me first define what is carbon neutrality. What it means is, having a balance between the emitting carbon and the absorbing carbon from the atmosphere in carbon sinks. And the goal of carbon neutrality, for which India has committed that by 2070 we will be, carbon neutral. The goal is to limit the temperature increase by the year 2100 to 1.5 degree to 2 degrees centigrade from the pre-industrial level. So this is what is carbon neutrality is all about. Now, this target to achieve this carbon neutrality is easier said than done. It would require enormous efforts to achieve this, and let's not have any doubt about it, because the way the things are going, we all are seeing the impact of climate change. We are seeing rising temperature, fall in agricultural productivity, flooding, unprecedented flooding in some areas, change in the monsoon pattern, change in the distribution of rainfall, a period of droughts extending somewhere, and somewhere we have excessively heavy rain, all of which are imposing a lot of difficulty in meeting this challenge of carbon neutrality. And the sad thing is that there is nothing that we can do about it by ourselves that will change this. This can only be changed if there is a collective global response to the impact of climate change. And this is what is happening in some kind of a global format where UN is involved, where India has committed to bring in carbon neutrality by 2070. Many countries have done it, committed for 2050. Now, so this is an important subject, and realizing the importance of this subject, Indian Association of Structural Engineers thought it prudent to bring this issue in the forefront of discussion in our fraternity. And with this background, we have invited an eminent structural engineer and an outstanding speaker, Mr. B.N. Hegde, to deliver a lecture on this subject, who will enlighten us by sharing his knowledge and wisdom on the subject. We also had invited two very eminent panelists with deep knowledge on the subject. Unfortunately, one of them, Dr. Ajit Sabnis, because of illness, is unable to attend today. But we have one panelist, esteemed panelist, Mr. Abhijit Kulkarni, who is the partner and director of structures in Bureau Happold. Bureau Happold is a established, well-known international firm uh, uh, doing a lot of good work on the sustainability. And if some of those participants who are regularly watching our webinars, I think last year we had Mike Cook from Bureau Happold who delivered a lecture which was jointly organized by IAS Tructee and Institution of Structural Engineers UK. So, ladies and gentlemen, this is our first webinar after the new governing council has taken over the reins of IAS Tructee. Our newly elected president is Dr. R. Pradeep, who is currently the director of CBRI. And I'm very thankful to him since, despite his extremely busy schedule, he agreed to grace this occasion by joining us. And before I request Mr. Hegde, the speaker, to take over the floor, virtual floor, may I request our president, newly elected president, Mr. Pradeep, to say a few words. Mr. Pradeep, Dr. Pradeep, please.
Thank you, Bhaumik-ji, for setting a good platform for this wonderful webinar on the very apt subject. Okay. So first of all, on behalf of all the members of ISTT, I warmly welcome everyone, each one of you who are attending this webinar. And you've already seen the a promotional video of ISTT. As it is mentioned in that, it is a apex professional body dealing with structural engineers. I request participants who are not yet members of ISTT to become members of ISTT, and those who are already members, I encourage them to participate actively in all the activities, professional activities of ISTT. Now, coming to the topic of this seminar, roadmap to carbon neutrality. As Bhaumik-ji just now mentioned, that India has already signed or made a promise that by 2070 will become carbon neutral. So in the race towards development and also competing with different countries aspiring for good ranks, somehow we lost the art of coexistence with nature. Just ignored that we are the most vulnerable species, that human beings. So now we are forced to think now. This 1.5 degree reduction in temperature is not a choice we have. We are forced to think about it. And you all know from the statistics right now, or from the numbers, world numbers, you know, India is a 5th largest economy and aspiring to climb up in the ladder. Maybe we'll soon take the number 3 position. So that means what? 3rd largest economy. Huge infrastructural activities, developments will take place in that. And again, it will be resulting in huge carbon emission. So this carbon or greenhouse gases, we have to understand, because India is currently the 3rd largest emitter of carbon. So this kind of webinars, I am sure, will first wake up from the deep slumber there in planning, designing, construction, as well as all the services which will be there in the building or any structure throughout its service life. So all the areas which are responsible for a structure or for a building, we need to think, because carbon neutrality as a topic should be there in our thinking very much. So I wish this webinar will throw a light and also will put seed in each one of us to think about it and achieve the desired target. So, and two eminent speaker, and then two panelists, one of whom is not present today for health reason. So I am sure both the speaker as well as panelists will be able to enlighten us on this subject. So thank you, Bhaumik ji, for asking me to give initial remarks. Thank you so much. Bhaumik ji, you're on mute.
Thank you, Dr. Pradeep, for your opening remarks, and I welcome you. This is your first, attendance in the webinar as president of IAS Tracti, and you are most welcome. I know that you are having some meetings and you will not be able to continue to be there for the entire length of this webinar, but we understand that and be there as long as you can. With this, I now come to the a situation where I have to hand over this virtual platform to the speaker of the day, Mr. V.N. Hegde. But before I do that, I have the privilege to introduce Mr. Hegde, whom I know for last, I think, more than 20 years. Mr. Hegde is the former Chief Executive Officer of Stup Consultants and former Executive Director of Gammon. He is now founder of a new consultancy organization, Decon Complete Solutions. He is a senior professional with rich experience of nearly 4 decades in construction sector in the areas of design management, technical management, site management, project management, and contract management of highways, bridges, energy structures, environmental, marine, and hydraulic structures. He is a recipient of around 17 national recognitions, in addition to an international prize from various institutions like IRC, ICI, NDRF, IBC, and IABSC Zurich. Recently, he has been conferred with FIB Fellowship, a coveted international recognition. He has been a strong proponent of sustainability and aesthetics in construction and has many publications on the same since 2000. Presently, he is spearheading a committee of IRC B5.3, bringing out the guidelines on the carbon neutrality for steel bridges. So, though this is a very brief introduction of Mr. Hegde, but I tell you, Mr. Hegde is unique in many ways because he is the one who is recipient of the Young Engineer Award from IABC Zurich. Perhaps the only person from India who received this award way back. And now, in first week of June, he is going to receive the fellowship of FIB again, something very unique because he is the only Indian, I think, who is being given this prestigious fellowship of FIB. It's an international recognition, and if you see, he has been very active in IAS Tracti. During the last 2 years, he has been spearheading and contributing immensely in disseminating knowledge through various workshops, refresher courses that we have been organizing. And I am sure I will be counting on Mr. Hegde for future also in IAS Tracti. With these few words, I will hand over this virtual platform to Mr. Hegde. Over to you, Hegde sir.
Thank you. Thank you very much, Alok, for introducing me. So I don't know whether I deserve so much, sort of an appreciation and admiration you have been bestowing on me. And my screen is visible?
Yes, it is visible.
Yeah. Just a minute. I'll see that. Yes, it is visible. Thanks a lot for an opportunity for me to give this particular webinar. As has been set out so beautifully by Alok as well as Dr. Pradeep, this webinar is a very, very important webinar. But unfortunately, we see for such sort of webinars, I've been participating in this IAS Tracti as well as other webinars and forums. the attendance is less. That itself gives a sort of an indication as to the importance we all give to this particular topic, roadmap for carbon neutrality in built environment for India. But going forward, I think it is not the economic criteria which will decide even for the businesses, for the structural organizations, whether it's a contracting firm or for that matter, even the consultancy firm. It is how to what extent the organizations are coping themselves or orienting themselves towards basically to the sustainability causes. I think it will become a part of the, like the business itself. Unless it becomes a part of the business, I think will not be really, getting up on that. Also, I'm very happy to see in this particular webinar, we have got an interesting, very, very expert domain in the sustainability. Mr. Abhijit Kulkarni is there. I was expecting Dr. Sabnis also. Both of them are experts in their field of sustainability, especially in the building sector, like that. And at the end of my presentation, I need to have a critical analysis of my presentation by Abhijit Kulkarni. I don't want the bouquets or flowers because, like I'm trying the subject, which is very difficult subject. It's also a boring subject for that matter. That's the reason we don't find many people participating in that. At this stage, at this nascent stage, it's a little bit theoretical also. That is why it becomes boring. Now, why we have to talk about the carbon neutrality in the environment? I think Bhomik as well as Dr. Pradeep has already set out so beautifully. And the climate change is no more a myth. All of us have understood in the beginning stages. All of us have heard that even the President of America, Trump, was saying that climate change is a myth. But I think I'm sure that even he is convinced now it's no more a myth. And also it happens because, like the carbon dioxide concentration in the environment, which is almost 410 ppm, it's going to be 500 ppm. And it is almost 50% higher than the pre-industrial era. This carbon dioxide concentration in the environment, how it's going to affect, we're going to see that. Most importantly, during 1960 to 1970, that's what we call it as industrial era, perhaps it was 1 ppm per year increase was there in that particular decade. But in the last decade, we have seen it has been increasing, concentration has been increasing yearly by 2.5 plus or minus 0.26 side. What is the result? The result is the manifestation, as Alok said, the super cyclone, change precipitation patterns, floods, droughts, wildfires, landslides, melting of ice, glaciers, avalanches, etc. All this manifestation is because of the temperature rise, what we call it as. That is the reason people are talking about if the temperature rise is more than 1.5 degree to 2 degree, especially the more than 2 degree, I think we see as some sort of an apocalypse. Apocalypse, pralaya, what they call it in Hindi, and that sort of situation. And with the present state of temperature itself, we have been seeing so much bad manifestations in the form of super cyclones, etc. That is the reason this particular slide explains the things properly. And to make the matter worse, our WMO has come out with a recent report in, I think it was on 17th May 2017 to 2023. And it says the coming 5 years, that is the 2023 to 2027, I think global temperatures are set to reach the new records. That's what it is saying. It's giving a figure. And that is what the worrisome is. Though after 2012 to 2020, we saw the record increase in the temperature in the last 8 years, as you can see on the right-hand side slide over here. But WMO is predicting in the coming 5 years, it's going to be again further recorded. So it's a matter of concern for all of us, because increasing this temperature will manifest in so many disasters as we climate change effects or the climate emergencies, as we have already seen that. So that is where we are here. So Between this year, 2023 to 2050, we have to tighten our belt and see that the climate temperature is not increasing more than 1.5 degrees. It should not increase even by the end of this century. As you can see here, 2100. And we have to take actions within 2025 to 2050 or 2023 now to 2050 in such a way that the carbon dioxide concentration in the environment will not increase, and also the temperature is always remaining less than 1.5 degrees. So if you really look at the predictions over here, this yellow predictions you should be having here, if you can see that, then only we can avoid what I call it as an apocalypse, like that. If it exceeds, say, for example, 2.5 degree to 3 degree, we are going to have an apocalypse. That's a kind of situations we are in. As Dr. Pradeep said in his opening remarks, we rank third in the carbon dioxide emission to the environment, and with almost around 2.5 billion ton carbon dioxide emission per annum, whereas China ranks second with 10.7, and the United States of America China ranks first, and the US ranks 48.17 billion. 4.81 billion. So this is how we stand. And in the built environment, we are today talking about, we are also contributing to the carbon dioxide emissions, as I said, and the built environment almost contribute to 40% of the carbon emission to the environment, out of which the building sector operation carbon itself, that is energy centric, for the operation carbon in the sense, I'll just come to that later. Basically, for operation of lifts and all this sort of things, that energy itself in the building sector 27%, it accounts. Whereas the infrastructure, materials, and the construction typically accounts for 13%. By 2030, it is expected that the steel, concrete, as well as the aluminum together will be accounting for 23% of the carbon dioxide emissions. Basically, in the built environment, cement, and my approach in this presentation will be, if we are able to control the carbon dioxide emission to the environment by controlling the cement, by controlling the contribution of the steel as well as the concrete, I think we'll be able to achieve the carbon neutrality in the built environment, in my opinion. I'm going to demonstrate that in my succeeding this one. So there were two very important milestone, like the United Nations meetings which took place, which is called the COP21 as well as the COP27, COP26. The COP21 was in 2015, which took place in Paris, where we had committed to reduce the emissions intensity to its GDP by 30 to 35%, and we also had committed, were committed for 450 gigawatt of renewable energy by 2030, and also the creation of the carbon sink or the carbon storage, what they call it, facilities for around 2.5 to 3 billion tons of carbon dioxide equivalent, and 40% cumulative electric power by the non-fossil fuel, that means renewable energy sources by 2030. That was the commitment in 2015 by our Prime Minister in Paris. Later, in very important meeting which again took place under the August of the United Nations in Glasgow, which is called as COP26. Famously, our Prime Minister announced Panchamrita for carbon neutrality, how we are going to achieve by the Panchamrita. That is, those Panchamrita were reduce economy carbon intensity by 45%, enhance non-fossil energy capacity to 500 gigawatt, and 50% of the energy requirement through the renewable energy, and also to reduce by the carbon dioxide emission by 2030 by 1 GT or 1 BT, billion tons, which out of the 2.4 which we are emitting at a particular point of time. And also in second phases, that is in the first phase, in the second phase, around 2070, we are committed to the world, or we are committed to this enhanced the COP26 to achieve our carbon neutrality, that is the net zero by 2070. So since 21 in Paris Agreement, we have already achieved quite a lot of milestones in the direction of achieving the carbon net zero carbon. And we in fact rank among the 10 countries in the world in the climate change performance index. Some of the actions which have been taken by us are been enumerated here, and that I'll not be going in detail as such. The most important thing for us to understand is we are already among the 10 top countries in achieving the climate change performance. Now, let us try to understand the basics. What is this carbon dioxide or the carbon dioxide equivalent in the built environment? Generally, carbon dioxide equivalent is briefly referred as a just carbon for the convenience, always. And it is a global warming potential in terms of kg carbon dioxide equivalent or a ton carbon dioxide equivalent. Unit could be anything, and in which it is a greenhouse gases what we talk about, the emission of the greenhouse gases. Apart from the carbon dioxide, there are other nitrous oxide gases and also the CH4 gases. But those are not that much. 90 to 95% in the greenhouse gases accounts for the carbon dioxide emission. And also this carbon dioxide emission, which has been emitted to the environment, stays in the environment for a long time. Unlike the other two gases, nitrous oxide as well as the CH4. Mind you, though it is in quantum very less, the other gases are more serious in polluting the environment compared to that of the carbon dioxide. But by controlling the carbon dioxide emission to the environment, indirectly we'll be able to control the CH4 and nitrous oxide also. So our whole objective when we are talking about is we will be trying to control the carbon dioxide emission to the environment, thereby CH4 as well as the N2 also. And this carbon dioxide, what we call it as, is also called as operation carbon as well as the embodied carbon. I think operation carbon is energy centric. Normally, you can see it in buildings more, like heating, cooling, ventilation, lighting systems, operation of the lifts, water pumps, common lighting, and use for the whole household appliances, fridges, washing machines. These are the carbon which has been used for the operation purpose of a building or a facility or an asset for that matter, infrastructure build. Normally, in buildings, 27% carbon accounts for the operation carbon. That's why I think over the period, by switching over to the renewable energy sources like solar energy, wind energy, I think this operation carbon in case of the building sector is reducing. But in a bridge sector, when I talk about the bridge sector, I'm talking about the infrastructure. Operation carbon is not to that extent. It's around 1 to 2% only. Say, for example, in the bridges, for the operation of the bridges, we do not require much electricity. That's how we look at it. So in building sector, the operation carbon is very, very important. What is the embodied carbon? The embodied is the carbon is expressed in different stages, which I'm going to explain to you as it is universally spoken. Embodied carbon factor is the direct global warming potential per unit of material. Say, for example, for for producing 1 ton of steel, if 2 tons of carbon dioxide equivalent is emitted to the environment, that is called the embodied carbon factor is 2. That's how we do reflect it. And normally we get the embodied carbon for a particular quantity by multiplying the quantity by the embodied carbon factor or the carbon factor per unit. As I explained to you, for producing 1 ton of steel, normally the carbon dioxide which is emitted to the environment is 0.8 ton carbon dioxide equivalent. It's reducing all over the world. 0.8 ton carbon dioxide equivalent for producing 1 ton of the steel is called the embodied carbon factor. Basically, it's a carbon factor. That's very, very important. At this stage, it is very important for all of us to know the energy produced or the electricity produced in our country, which is basically used in the infrastructure. Of course, in the other sectors, I think there are solar energy, wind energy, etc. Infrastructure where we for manufacturing of the steel or the manufacturing of the cement, we require the electricity basically or the energy. That energy is normally obtained by the thermal power plants by burning the coal, which we call it as a fossil energy. And the carbon factor embodied the carbon factor for the fossil energy as recorded in the source, the government sources version 6 of CEA, Government of India, is 0.85 kg carbon dioxide equivalent per kilowatt per hour. That is 236 kg carbon dioxide equivalent per gigajoule. That means when we are using the electricity also, we convert that electricity for producing some certain material into the carbon dioxide emission to the environment. So that is how even when you are using the electricity, which is coming out of the fossil energy, that is the fossil sources like coal, burning of the coal also gets converted into the carbon dioxide emission to the environment. That's how it is calculated. This is just, I just wanted to give you the fundamentals before that. Now coming to this, basically this, there are standardization which has been evolving over the period, almost 10 to 15 years, since 10 to 15 years. And the very important standardization is the CEN TC 350, Sustainability of Construction Work Assessment of Buildings and Civil Engineering Works. The European standards have come out, the 15643 series, like the series with one is related to the general framework, 6432 is related to the framework of the environmental performance, and 3 is the social performance, and 4 is the economic performance. What we are going to talk about when we are talking about the carbon neutrality in the environment, basically we'll be talking about the 15643.2. That is a framework for environmental performance, which also gives the calculation methods and also to how to work out this environmental product declarations. So what is environmental product declaration? I'll just come to this later. So it's a sort of a Bible, these guidelines of the European guidelines. And also there are equivalent ISO guidelines also on that for basically looking into the sustainability of the construction works for the assessment of buildings as well as the civil engineering works. It's a very, very important for us to understand basically the life cycle stages as defined by BS EN 15978. This has been followed universally in calculating the carbon throughout the life cycle of an asset, whether it's a building asset or an infrastructure asset for that matter. If you see this particular model, which has been given for the life cycle of an asset, and basically the embodied carbon has been divided into 3 stages. One is the upfront carbon, what we call it as. Second is the embodied, the in-use stage carbon. Third is the end of the life stage carbon. And the upfront carbon consists of the product stage as well as the construction stage. Product stage in the sense it for the extraction of the raw material itself, for the manufacturing of the raw materials, when it is being manufactured, as well as the raw material is extracted, say by mining, it has to be transported also. So for whatever the embodied carbon is there, which is called the product stage embodied carbon, it has been expressed in terms of 3 modules called A1, A2, A3. Similarly, at the construction stage, there are 2 modules, A1, A4, and A5. One relates to the transportation, and the second relates to construction process itself. In case of the steel structure, fabrication, transportation, as well as the erection. That is the construction process. In case of the concrete structure, concreting, and those sort of things comes into the picture. Most important thing is also the in-use stage. In-use stage also the carbon dioxide emission to the environment continuously takes place by use of the facility, by maintenance of the facility, repair of the facility, replacement of the facility, as well as the refurbishment. Say, for example, our bridges are designed for 100 years. Within this 100 years, after completion, after the facility is completed by virtue of its construction, the bridge has to last for 100 years, because the 100 years the service life. During that 100 year, whatever the carbon dioxide emission is taking place by virtue of maintenance, repair, rehabilitation, and refurbishment, this has been calculated in this in-use stage. Once in-use stage is over, the 100 years in case of the bridges is over, the end of life stage will come. Once it is 100 years over, we'll have to dismantle it. We'll have to use it for the landfill, for which the transportation has to take place. All these processes requires not requires, it makes the carbon dioxide emission to the environment. That is how it is calculated. So from upfront carbon to the in-use stage carbon to the end of the life stage carbon, all this carbon together is called the whole life carbon, or the whole life cycle carbon, basically. And after that, the end of the life stage, this can be used, reused, recovered, and recycled. Like the design of a structure or a facility can be made in such a way, even after the 100 years, the material can be reused. For that, the credit is given for the carbon footprint. Normally, say, for example, if you are using a steel as a structural material for the construction purpose, 90% of the steel can be salvaged and reused again. So to that extent, some sort of a credit has to be given to this, and the carbon footprint for the steel structure will reduce to that. That is called, what we call it as a circular economy. Basically, whenever we talk about it, we call it as a circular economy. All these stages also normally is represented by boundary systems, what they call it as a boundary system. You can see here from the cradle, it starts cradle to up to the module A3, it is called the cradle to gate boundary system, and cradle to model A1 to A5 is called the basically the cradle to the completion boundary system, and till the end of the stage, it is called the cradle to grave boundary system. And once it is there, if the circular economy is used in calculating the embodied carbon, then it is called the cradle to cradle. What is the embodied carbon? That is how this life cycle stage defined by BS EN 15978 is normally being operated. It is done universally now. It's a sort of a Bible for calculation of the carbon in the environment now. As per this Indian Institute of Structural Engineer, UK, they have given the guidelines as to how to calculate the embodied carbon. For the building sector especially, they have already given what's happening in the world. We can see here again, the maximum is normally, whether it's a building sector or a bridge structure, for that matter, the maximum embodied carbon or the carbon dioxide emission directly to the environment takes place during the product stage itself. That's a A1 to A3 module, as you can see here. Particularly in building cases, the operation carbon, as I explained, is very high compared to that of the bridges or the infrastructure, as you can see here later. There is a slight difference as far as the infrastructure is concerned, and instead of only A1 to A5, the infrastructure introduced another stage because the infrastructure requires the preliminary studies. Unlike in the building sector, the carbon dioxide emission which is taking place because of the preliminary studies also added. Another module is added in the upfront carbon stage or a product stage, as you can see here, which is called A0 module, as you can see on the presentation over here, on the slide over here. In the use stage, instead of only having B1 to, if you really look at the building sector here, we have got the module B1 to B7, including the operation carbon for the operation energy as well as the operation the water. When you come to the infrastructure, That is, say, for example, the bridge, we have not only up to B7, another two modules get added. That is a B8 and B9, which is the other operational purposes, and the users utilization of the infrastructure also get added. So for the infrastructure, more number of modules is there compared to that of that. But otherwise, there's not much difference between the life cycle stages for the infrastructure as well as the buildings, as you can see here. So I think I have defined here what is the whole life of carbon, what is the upfront carbon, and also the in-stage carbon, in-use carbon, end of the life carbon, and also the cradle to cradle. That is what is the circular economy is concerned. So I hope that the fundamentals so far, which has been explained, has been understood well. It's very, very important for us to understand these fundamentals and some of the terminologies which is there universally to understand how to achieve the carbon neutrality in the built environment. Now, first step is normally to calculate the embodied carbon, and there are many guidelines are available, and the latest guidelines is how to calculate embodied carbon by IStructE, that's an institution of structural engineering UK, and also there is an inventory of carbon and energy by the ICE, which is a very, very important document. It is more user friendly, and it gives the inventory of the carbon as well as the energy. It gives the embodied carbon as well as the embodied energy for the various construction materials, whereas IStructE document, that is is combining the embodied energy, embodied carbon by virtue of the embodied energy, and giving a single version. I think that may not be very useful. It's very important for us to differentiate the carbon which is getting emitted due to the direct carbon emission due to the processes, the manufacturing process itself, and also the carbon which is emitted by virtue of the electricity used, which is called the embodied energy. I think it's very, very important for us to understand. Here, what you see, the definition for calculation of the embodied carbon, especially in the upfront carbon stage, is my own notation. You can see here, EC direct. What I call is the construction material emit greenhouse gas directly to environment during the production process, which is called the direct embodied carbon, which I call it as. It is for enabling the calculation methodology or making the calculation methodology easy. I have sort of given a nomination to that, like EC direct, and also the energy used to manufacture the material emit greenhouse gases when being produced, which is called embodied energy. For the purpose of the presentation, the carbon factor, because of the embodied energy, is denoted here in this presentation as EC prefix EE. That means embodied carbon by virtue of embodied energy. Basically, that's how I put it at. And also there are carbon factors which are denoted by EC transportation, embodied carbon because of the transportation of the materials which is taking place from one end to the another, and also the embodied carbon because taking place because of the construction, which is denoted here as a EC construction, as you can see here for the purpose of that. Now, as I told you that there are various data bank is available for the calculation of the embodied carbon, inventory of carbon and energy by ICE, I think is the most important document. On the basis of that, and also on the basis of my experience, I have compiled here some of the carbon factors. You can see over here embodied carbon for the different materials which is used in the construction over here. That the embodied carbon from A1 to A3, that is the product stage. Embodied carbon from embodied energy for A1 to A3, and also in India, basically on the basis of the experience which I had during my working experience, I have noted down here the embodied carbon per ton transportation of various materials here. Say, for example, fly ash for transportation of 0.1 ton of fly ash 1 kg of fly ash, this is required is 0.036 kg carbon dioxide equivalent per kilometer. That's how I have given it here. That's how the calculations is taking place. And also for the, normally what happens is basically when you have to under the modules A4 and A5, that's the transportation model as well as the construction process model. Basically, the embodied carbon arises out of the operation of the equipment. And for the operation of equipment, how much fossil fuels are required for the different kind of equipments basically has been given. Here it has been compiled as well as given. Say, for example, in case of the batching plant, 30 cubic meter of the batching plant, if you are running, it may be operated through the electricity, which is available. If it is an electricity, it requires 0.252 gigajoule per hour. So I think you can calculate for producing the concrete, like you can calculate for construction, for calculating the embodied carbon for the construction under the A5 module, basically it has been given. So this is how the carbon factors which has been compiled over here for the various construction materials, whether it's used in the buildings or in the infrastructure has been compiled. Once you get that, I've just given an example over here, like I had taken the example how to calculate the embodied carbon. I've taken an example of a bridge structure over here, and it is a rehabilitated foundation, which has both the well foundation as well as the pile foundation. The well foundation, which has been tilted beyond the permissible tilts and shifts, has been strengthened by the pile foundations. The piles, as you can see here in this particular example, and 8 number of 1.5 meter dia piles, almost around 40 meter length, and the concrete grade is for both the well foundation as well as the pile foundation here is M35, and the pile cap has to be done, the pier has to be done. It just been strengthened over here, and so that I can give the calculation methodology for both. Just to explain here, the methodology is very simple. First, you will have to calculate for production of 1 cubic meter of concrete, how much carbon dioxide emission takes place. Using the carbon factors, which I have given over here, that has to be multiplied per cubic meter. I can work out what is the carbon dioxide emission which is taking place. That is the embodied carbon per cubic meter of concrete of M35 grade here is worked out is around 0.963, and adding 5% carbon wastages using different methodologies, it becomes around 1.025 for this particular foundation over here. Similarly, you will have to work out for the reinforcement steel as well as the structural steel. Structural steel is used here in the cutting edge. In case of the well foundations, all of you are aware of it. So that also you'll have to take the carbon dioxide emission. It's not a temporary work, it is there. So first you'll have to work out the product stage for the concrete as well as the steel. What is the carbon dioxide emission taking place? Once you have done that, and you'll have to come to this, to the construction stage, A1 to A3. You know here A1 to A3 stage, that's the product stage. You have got a total cubic meter of concrete in the well foundation. That concrete multiplied by the embodied carbon factor per cubic meter of the concrete, you will be getting the embodied carbon for the entire well foundation. And similarly, you will getting for the pile foundation also, how much concrete is there. And also the reinforcement steel, you already worked out per ton of the reinforcement, what is the embodied carbon. Using the embodied carbon factor, you know that. So totally for product stage, you will get around 3,629.56 ton carbon dioxide equivalent, as you can see here. Now you come to this construction stage. How the well foundation is done? Well foundation is done by sinking and also producing the concrete. The produced in the batching plate has to be transported to the where the well sinking is done. For that 30 cubic meter of concrete per hour, how much capacity batching plant for the construction of concrete is calculated. And using that, you work out what is the carbon embodied carbon for that. Similarly, transit mixer is used for transporting this, and you can work out what is the embodied carbon because of the transportation here. For sinking of the wells, you use the cranes, and by using the crane hours and the consumption of the fossil fuels, you can straight away convert into the carbon dioxide emission. That's how you can do it. Similarly, in case of the pile foundation, also you can use the piling rigs are used, and for the handling of the reinforcement cages, normally you use the cranes. All this together, in this particular case, where the pile come well foundation over here, you can see that the product stage, that's a direct product stage carbon from A1 to A3 is 3,629.56 cubic meter ton carbon dioxide equivalent, whereas for the construction stage, it's only 22.8. That's almost around 0.6%. So in India, what we are seeing, especially for the superstructure, normally it comes around 1 to 2%. Basically, during the construction stage, carbon dioxide emission for the infrastructure basically takes place. There are different ways of working it. In case of the building, normally the benchmarking for this embodied carbon is done on the basis of the unit area and the structural element wise, material and the structural system wise for the different combination. That's how normally in the building it is done. And Dr. David Collins, he has also tried to present along with the many other authors for even for the bridges on the linear meter basis to present the carbon embodied carbon. Say, for example, you've got a simply supported bridge, continuous bridge, integral bridge, and also suspension bridges, cable stay bridges. And for the different kinds of the typology of the bridges, he has tried to give in terms of the per meter length of the bridges, what is going to be the carbon factor or carbon footprint. I don't think that's the right way to go about, because in case of the bridges, basically what happens is the foundations are highly carbon intensive compared to that of the buildings over here. Any kind of this kind of approach may not be a correct approach, and the variables are the number of BOQ items, or the items in case of the bridges is not as much as of the as that of the buildings. In view of this, I recommend that the carbon calculation for the infrastructure projects, especially for the bridge projects, has to be done from the first principle itself. It's not very difficult to do it. It's very easy to do it. And it is not possible for us to benchmark it on the basis of the linear meter of the bridges or the square meter of the bridges for the different kinds of the bridges. It depends upon the foundation types we are going to have, and the foundation is carbon intensive, as I explained to you. Now let us come to this carbon calculation in use stage. As I explained to you, for the use stage, as you can see here on the right hand side, the top slide, use stage has use, maintenance, repair, replacement, as well as the refurbishment. That is how it is. Normally, the bridges are designed for 100 years. I think the buildings, I don't think the service life is given. It's around 50 years perhaps, and that it is there. And you have to have a maintenance regime or the maintenance plan. It has to be decided, basically. During this service life, as you can see here in the right-hand bottom corner slide over here, this is the service life. After the completion, this is the up to the end of the life, the service life, and on the basis of the deterioration models which we have, the performance of the durability goes on, like decreasing after some time, as you can see here. Once it decreases to certain level, to again, increase the performance to the required level, again we have to repair it or we have to maintain it continuously. So the continuous maintenance also incurs in the carbon dioxide emission to the environment. That happens for the 100 years in case of the bridges, as I say that. And also we have observed that in case of the precious concrete bridges and the other bridges which has been in surveys, I think already the couple of bridges have been replaced after 40 years itself. And also sometimes because of the extreme events which has been taking place because of the climate change effects, or otherwise also, cyclonic effects, tsunami effects, and earthquake extreme event effects, the structure may collapse and we may have to rebuild it. In fact, the entire city, this is the photograph you can see here. it is the Turkey earthquake which has taken place, and certainly those structures which are there, which have fallen down, have not served its full service life. As such, it has to be rebuilt. When it has to be rebuilt, enormous carbon dioxide emission takes place, as you can see here. So in use stage, if you really want to really control the carbon dioxide emission to the environment, it has to be designed as a resilient structure, especially for accounting for the climate change effects. I think we'll have to come out with the guidelines, the probabilistic models to account for this climate change effects, for the resilience of these structures. And also the durability design is very, very important. We'll have to design a structure that it lasts for the entire service life. Otherwise, the structure may corrode, a structure may deteriorate in between, whether it's a building or whether it's an infrastructure or a bridge project. When it deteriorates beyond the performance requirement level, it has to be repaired, refurbished, and sometimes it may have to be replaced. All this involves the carbon dioxide emission to the environment, and the durability of the structure is very, very important going forward for achieving the carbon neutrality, as I will explain later in my further slides. So I've explained here that the carbon dioxide emission to the environment in use stage as well as the upfront carbon state, that's the product as well as the construction stage. Now, how do we achieve carbon neutrality in the built environment? Let us understand first what is the carbon neutrality we are talking about. As we are committed to the COP26 in Glasgow. We have committed as a nation to achieve the carbon neutrality or net zero carbon to the environment by 2070. How to achieve it? And here is a model. You can see here what I call it as EARS model, EARS model. First, you will have to estimate. I showed you that how the calculation of the embodied carbon at the different stages can be done. That has to be done. The calculation of the carbon footprint has to be done first. Then we'll have to see whether it's possible to avoid the carbon footprint itself. At many of the cases, say for example, in the built environment, we have to use this structural steel. We have to use the cement and the concrete for the construction. That's a major building materials. It's unavoidable. So whatever is possible for us to avoid, say for example, replacing the cement by mineral admixtures like slag and GGBFS, I think will be reducing the carbon footprint or the carbon emission to the environment. That has to be done. That's how it can be avoided. When it is not possible for us to avoid it, reduce it. That's the next step. Reduction in the critical mass of the structure itself. Basically, we can think about by design, value engineering, etc. And how do you reduce this carbon footprint to the environment? We'll have to see. What we are not able to reduce, we'll have to set off by the circular economy. That circular economy model by reuse, recycling, and remanufacturing. That's how we have to see that. By doing reusing, recycling after the end of the life cycle, what we normally do is to give the credit to the carbon footprint. In the sense, we'll minus it. That's how we'll calculate the life cycle carbon footprint. So that's how it is set up. All these things, whole thing is called the carbon neutral. That's how we achieve the carbon neutrality. So the carbon neutrality is a process where greenhouse gas emissions are brought to net zero by avoiding, reducing, and setting up those emissions which cannot be avoided and reduced. That's how I define this carbon neutrality in the environment, and we will have to achieve that even in the in our built environment too. Now, this cannot be achieved or done by the business usual approach. I think we'll have to have consciously we'll have to do it. All the stakeholders together, it has to be done. Here, my approach basically in achieving the carbon neutrality, which I'm presenting, is by controlling the carbon emission to the environment, by fully controlling the carbon emission in the concrete as well as the steel. Basically, I feel that the building in the built environment, as a building material, steel as far as the carbon, steel as far as the concrete is extensively used. Of course, in buildings, aluminum is also used. I understand it's around 1.5% aluminum is used. So by controlling the carbon dioxide emission in the concrete as well as the steel in construction as well as the product stage, I think we'll be able to achieve the carbon neutrality in my opinion. And as per the World Economic Forum Net Zero India tracking, if you really look at it, around 5% steel is India is producing of the world, producing of the world. Here is around 5%. And around cement, 8% cement is being produced by India in the world. And if you directly calculate the carbon dioxide emission because of this steel as well as the concrete, you can directly calculate it according to my this one, that is 120 million tons of the steel is being produced in 21-22. As you can see here, normally around 50% of that is basically used for the construction worldwide, and India is not very different. It will be the same. 60 million tons of the steel is used in the built environment, as you can see here. And if you calculate the total carbon emission is around 545 million ton carbon dioxide equivalent. That's around 5%, which is very, very, very much matching with the World Economic Forum, that estimation. As you can see here, because of the steel, India is emitting around 5% of the carbon dioxide as in the built environment, as you can see here. And the cement, similarly, it's 379 million tons of the cement is used in India, and which emits 795 tons carbon dioxide equivalent, as you can see here. According to my calculations, around 12.6%, we are emitting carbon dioxide. We are emitting in terms of the concrete contribution to the contribution out of 2.5 GHG gigaton of that, 12.6%. But it is not matching with the 8% production, which has been estimated by the World Economic Forum. We are slightly on higher side, 12.6%, according to my calculations. So the World Economic Forum also says the worldwide by 2050 in cement as far as the concrete. The world also is talking about, when we are talking about the carbon reduction in the built environment, there is also talking about the reduction in the concrete as well as the steel, since it's a major building materials. And the global carbon dioxide emission in the world is 2.5 gigaton, and the global carbon dioxide emission in the steel is 2.7 gigaton. Basically, out of 2.7 gigaton, around 50% is because of the construction of the built environment, as you can see here. Presently, the world average, as you can see here, is for producing 1 ton of the steel, 1.9 ton carbon dioxide emission is taking place to the environment. Whereas in India, it is reported around 2 to 2.5 ton carbon dioxide emission for production of the steel. And it is estimated by 2050, as you can see here, they are estimating, or they are projecting, or they are planning to reduce the carbon dioxide emission, direct carbon dioxide emission to the environment for producing the steel to only 0.11, that is 1.9 to 0.11. Similarly, for the steel, cement, for the World Economic Forum projects that the potential of reducing the direct carbon dioxide emission by 2050 is around 0.03 ton carbon dioxide equivalent for producing 1 ton of cement, whereas presently world average is around 0.6. Whereas in India, I'm told it's around 0.8 to 0.9 ton carbon dioxide equivalent per ton production of the steel. That's how the world is targeting it, is planning to reduce this carbon dioxide emission to the environment in the production process itself, as you can see here. Now, what are the strategies worldwide if you have to look at it, what are the strategies adopted for achieving the carbon neutrality by 2050? It is the all except for India, all the other countries are planning to achieve the carbon neutrality by 2050. We have given the target of 2070. And in concrete sector, that is a figure of the global concrete as well as the cement association figure you can see here. This is you can see here they are achieving the carbon reduction by the various processes, as you can see here. Efficiency in design construction around by 22%, efficiency in concrete production 11%, savings in cement and binders by 9%, savings in clinker production by 11%, carbon captive and capture CCUS basically is around 36% is by the CCUS. The Global Cement and Concrete Association is targeting to achieve this. And of course, in I could not get anything from World Steel Association as to what is their target, but British Constructional Steel Association has got this. I really liked it because it's easy for me to also work out the roadmap for the carbon neutrality using this. As you can see here, by design efficiency in the steel structures, they are planning to achieve reduce the carbon by 17.5%, and circular economy by 15%, direct carbon emission to the environment 28%, grid decarbonization by 6.5%, and CCUS again all over the world. I think the attempt is to achieve this carbon neutrality is more through the CCUS. I'll come to that, what it is, CCUS is. And of course, by the construction process, only the 8% they want to do it. That's how it is done. Having the same approach, when I try to calculate for India as a roadmap for achieving the carbon neutrality, now I just, at the product stage itself, including the construction, I worked out the carbon, emission, carbon footprint percentages actually in the first stage, that is the EC direct during the production stage. In the concrete construction, 38% takes place, and by reducing in India 0.9 ton carbon dioxide equivalent to 0.3 ton carbon dioxide equivalent, whereas the world is trying to achieve it 0.03. I have only put the target of 0.3. It's possible for us to reduce around 25% in the direct carbon emission by reducing through the process of production of the cement itself. And by decarbonizing energy, see, I have a discussion with a lot of people, and though we have saying that we'll be able to achieve the electricity production by 2070, the entire by switching over to the renewable energy sources instead of fossil energy. But I think it's going to be a very challenging task. I think by 2070, I think we'll be able to achieve only 40%. We'll be able to switch over, in my opinion. Even if we take 40%, I think it's possible for us to reduce in the concrete 23% reduction in the carbon footprint, or the embodied carbon, basically. Decarbonizing, like normally for running the vehicles or also running the equipment, you require the fossil fuels, and by decarbonizing it, even that by 40%, out of the 4% during the construction, it's possible for us to reduce 1.6. Whereas the rest, this is the balance which you are left out of it. Out of the 100%, this is the balance which has been left, and we have to achieve it by credit. In case of the concrete, we have to have the mixed designs in such a way at the end of the life. I think we should be able to have around 30% recycled aggregate. We should be able to use that recycled aggregate in manufacturing of the concrete. So if we give 30% for the recycling, that is for the circular economy, we'll be able to achieve around 11.5% reduction over there. And design efficiency, including alternative materials like alternative materials, in the sense we can use GGBFS, calcined clay, and so many other alternative materials instead of the cement itself. In the concrete, I think it's possible for us to achieve 15%. And of course, the rest CCUS will have to achieve, but there is no other option but to go for the 24% for that. Similarly, I have worked out for the steel also here, how we will be able to achieve the carbon neutrality on the basis of the distribution of the embodied carbon percentages in various stages. This is for the the carbon neutrality strategies for the concrete infrastructure. The same calculations has been explained here. By design efficiency, we'll be able to achieve 15% in the modules A1 to A5. By circular economy, we'll be able to achieve 11% for the concrete. By decarbonizing energy, I think we'll be able to achieve for the concrete sector 23%. A direct carbon reduction at production stage, it's around 25%. Basically, it's 0.9 ton carbon dioxide equivalent for producing 1 ton of cement. If it's brought down to 0.3%, 0.3 ton carbon dioxide equivalent, we'll be able to achieve 25%. Of course, by CCUS, we'll have to achieve it around 20% for the concrete structures, whereas for the construction processes, basically transportation as construction will be able to achieve 1.6%. So by this, in 2 phases, by 2070, we'll be able to achieve the carbon neutrality. That's the carbon footprint, in my opinion. This is the roadmap which I am suggesting for the concrete structure. Similarly, I have suggested, only thing is we'll have to see here that the renewable energy 28%, and as far as the CCUS, it's becoming around 15%, as you can see here for the steel structure. Slight variation is there. The design efficiency is also not 15% compared to that of concrete. In concrete, 15% because there is a possibility of using the alternative materials much more than in concrete than in the steel. But if you can see here, the circulation in case of the steel structure, the circular economy is very high because it's possible for us to get the credit up to even 90%. All the steel structure can be recycled and it can be used again. A lot of credit will be given. It is a highly recyclable and reusable material. That's why the carbon neutrality, the percentage in steel structure is much higher than concrete structure, as you can see here. It cannot be achieved by one stakeholder, one designer, or an owner, or a builder, for that matter. It's a whole effort. It's a connected construction, basically. All the stakeholders have to contribute to this efforts of carbon neutrality if we'll have to achieve this by 2070. There is a very interesting supply chain diagram which has been given by Ian 15978, where it used as responsibility metrics at different life cycle stages, as you can see here, and the various stakeholders. Say, for example, it's very important to see here the scope 1 and 2 is the primary responsibility, and the scope 3 is the secondary responsibility, sort of that. Designer has a role in all the life cycle stages, as you can see here. This is the important point I just wanted to know. Though it's a sort of a secondary responsibility, the designer has a role. These designers are involved throughout the life cycle, or a whole life cycle, life carbon, and are therefore required to provide low carbon and decarbonization proposals in the entire life cycle analysis, as you can see here. Designer's role is very, very important. So that we'll have to really put into one note. Now I'll just come to this, some of the responsibility of the various stakeholders with some illustration I will try to give here. Most important thing is the carbon factor data, inventory of carbon as well as the energy. On the basis of the model which has been proposed by Dr. Akiya Kasuga, I've just modified the sort of a structure, how the carbon inventory, carbon as well as the energy inventory in Indian conditions can be done. And we have to have a repository for that. Right now, there is no repository in India, and the International Finance Corporation in 2017, tried to collect some data in consultation with the manufacturers as well as the suppliers. In fact, they consulted developers, but it was not widely consulted. It's only few. They try to but I think it's in the work in progress. It's not a much helpful as I can see here, but I am proposing a structure how it can be done here, and the repository could be MOEF, like the Ministry of Environmental and Forest, and the suppliers, designers, builders, and owners, they can give the information. There could be a regulatory framework, and it can be certified by the third party. There are so many certification agencies as such, and for ultimately these carbon factors can be a data bank or an inventory can be created. And also the association while collecting this data can be done using some calculators which are available, like ICE is there, iStruct is there, EC is there, Econvent is there, and there could be an association with all these people. And also the collaboration could be with existing databases as well as the EPDs, what they call it as environmental product declarations. I'll come to that. It's very, very important. And the collaboration could be with the EPD, Global Cement and Concrete Association, CARES, ECSN, etc. For the material maker, for the equipment maker, as well as the facility maker. This is how it is done. It's very, very important for us to estimate the carbon, existing carbon, unless the data or the estimation is there of the existing carbon footprint. I think it's impossible to achieve the carbon neutrality. So the first work which we have to do is we'll have to create a repository or a regulatory framework wherein all these carbon factors has been done and it is kept at one repository. This is my structural proposal for doing the same. What is environmental product declaration? I think many of the people, many of the agencies in some of the countries, the environmental product declaration has become some sort of brought under the regulatory framework. Unfortunately, in India, it is not. Though some of the agencies or some of the manufacturers themselves, they are enrolling to this environmental product declaration program at the different stage, as you can see here. And in fact, ISO 1425 is a referred document for the environmental product declaration, but that was available in 2000. During the 10-year span, differences and controversies in the declaration document led to the introduction of rigorous rules for the building sector in EN 1518-4, as you can see here. But as I explained in this my structure, it's very necessary for us to, bring this under the regulatory framework, as you can see here. This is one of the example how it looks like. This is how it looks like. This is for one of the projects of steel. You can see here climate change potential unit is given for one of their product. This is how it gives. It's obviously a steel sections or a steel component, as you can see here. They are given minus 1.48 in the D. That the D is nothing but the after the life stage. That is the circular economy stage. For the circular economy, they have taken 1.8 E. So not only the carbon warming potential it gives in terms of the kg carbon dioxide equivalent, it gives so many other details also, as you can see here, whether it's a nitrous oxide as well as the other. So it's very important for us to bring some sort of a regulatory framework for estimation, declaring this environmental product declaration by all the agencies who are involved in the construction. It's very necessary for us to achieve the carbon neutrality. Another like this, what I'm suggesting for the policymakers is to really bring in the tendering procurement process itself the concept of the sustainability into consideration. Now we have presently the DPR, AE, authority engineering consultancies, also the PMCs are done on the basis of the what we call it as a QCBS system, quality cost based system, where 70% weightage is given to quality as well as the 30% weightage is given to cost. But it's very, very important for us to bring this QCBS system, not only this consulting procurement, even to the contracting, EPC contracting procurement too. Is very, very important. What I am suggesting in this whole EPC contract model, as well as the consultancy model here, that what I call it is a QCSBS system, where quality, cost, sustainability system, what I call it as, where the weightage should be respectively given to 40, 20, and 40. And it has to be extended to the EPC contract as said. Unless it is done, I think the relevance of this achieving the carbon neutrality in the built environment will not be understood. Even in the building sector also, I think we'll have to have some sort of a, regulatory framework where not only to the quality or the cost, even to the sustainability also some sort of a weightage is given. I think that's how we'll have to proceed. If this is done, I think 50% of our problem of achieving the carbon neutrality is solved, in my opinion. Standards and code making is another issue. It's again a policy making sort of an issue. Very important. We'll have to have a relook at our safety factors and the over specification of the load factors. And also we have to move into the performance based specification from the prescriptive specifications as early as possible. And we have to come out with the guidelines for extending the life of the bridges and the other structures in view of this extreme events which is taking place because of the climate action, climate emergencies. And also, there are some small things like, allow composite piles, allow pile putting in the infrastructure, which will reduce, carbon footprint to a large extensity. But unfortunately, we have some sort of idiosyncrasy in our code makers as well as the policy makers, that the construction deficiencies have to be factored in factor of safeties. As such, we'll have to have high factor of safety in India because the construction quality is very less. I think, in my opinion, in the era of sustainability, that is unfounded, and it is not apt to do that. That we'll have to really look into. And these are all very well known aspect to increase the size of the aggregates, as you can see here. And of course, our new IS 383, it suggests as to how to use the slag aggregates, steel slag aggregate, copper slag aggregate, construction demolition, all is permitted, and it's encouraging a sustainable aspect. And a restriction on a use of mineral admixtures, which are industrial waste as a byproduct, should be totally removed. I think even our codes, whether it is IRC 112 or highway code for the PQC, still put the restriction on the use of the mineral admixtures like fly ash as well as the GGBFS. In my opinion, there's need to review that. Of course, there are the issues like the score depth calculations. I think this I've explained quite a lot in so many other forums. So that needs to be looked into. There are instances where like using the silt factor, we have done the calculation of the score depth in the rock. It's not possible for a foundation to go up to that depth. It results in totally unsustainable and the carbon intensive carbon footprint will be added because of that. There are some codal interpretations sometimes like that helps in increasing the carbon dioxide emission to the environment. As you can see, it's one of the bridges where our Mr. Bomik, our moderator, was also involved, and just because there was a sentence in the codes like the depth of the foundation shall not be less than those of the existing structures in the vicinity. And there is an existing structure, existing bridge over here, and there is another new bridge which is under construction over here. Design wise, even though the depth of the foundation was 10 meters, it's a highly carbon intensive foundation. The well foundation 10 meters higher, but I think it was insisted upon just because of the sentence is there, that in the code. I think we'll have to really relook into this, review this sort of codal specification. And the result is enormous carbon dioxide emission and enormous energy consumption, as you can see here, that could have been avoided. So we have to really look at it. This is in the rock, score depth has been specified, and after 20 years in both these bridges, one is the Tapi bridge, another the Pasighat bridge, since there was a score depth calculation, the rock which give the almost 20 to 30 meter penetration into rock for the well foundation. It could not be done. Ultimately, it has been raised for 20-meter by blasting, by sinking, by all these sort of things, the carbon dioxide emissions which takes place. So these are the sort of codal specification, codal provisions we really need to look at. Especially in the IRS, the Indian Roads Services Codes and Standardization. There are 3 codes running parallel in India: BIS, IRS, as well as the IRC. All of you are aware of it who are attending that. And there are many conflicting provisions in 3 code systems. There's a strong need for us to rationalize that, basically. And also, I feel that the IRC code making is more vibrant and more updated. It's up to the international level. I think similar to that, I think IRS as well as the BIS code making also has to become. In fact, recently I'm seeing the BIS doing a good job. I think it's unlike earlier days. What I see here is there are some provisions, like in IRS codes. Say, for example, it says for the piles, you cannot take the friction capacity. You have to only design it for the end bearing, though friction capacity is available. And it prohibits the use of mineral admixtures. I think in the era of sustainability, prohibiting the use of mineral admixtures for the railway projects, it's a crime in my opinion. I think it will not allow for us to really achieve the carbon neutrality if the mineral admixtures like fly ash, slag, and calcined clay, it's going to be there in future if it is not allowed at all. And because of that, I was investigation one of the cases, just because this mineral admixtures like slag as well as GGBFS, in this particular case, you can see here, this is a bridge which is already constructed on a well foundation of 14-meter dia, around 20-meter depth over here. And there were vertical cracks in the staining after the installation of the superstructure, as you can see here. And the cracks was investigated, and the cracks were found to be in the bell cap too of around 2.5 meter thickness, and also in the upper lifts of 2.5 meter each. There were around 5 to 6 cracks, and some of the cracks were going through and through the staining. And my investigation revealed that it's basically because the heat of hydration, the shrinkage which is taking place during the concreting, because the mineral admixture is not allowed or the permitted in the mix design itself. It's not only making the concrete carbon intensive, but also it's not making the concrete non-durable. And also, we'll have to be very careful while making the code. The IRC code, which is meant for the structural design, has deleted the clause for the minimum percentage of the steel to be provided for overcoming, for taking care of the shrinkage as well as the temperature during the casting. The clause was there earlier, and that has been deleted in the latest cost. And as such, there is no clause in the IRS code for the minimum percentage of the steel, and the 0.12% in the staining for the PCC has been used, and 0.04 transfer direction is used. That is not meant for the minimum percentage of steel. That steel which has been given in the code is for holding one unit of the staining to the another unit of the staining during the casting. Basically, that's what it's meant for. By removing this clause, there is no clause at all for the provision of the minimum percentage of steel in the PCC when the well is designed as a PCC. These are the sort of anomalies I think we'll have to take care of while making the codes, while doing the code making, codes and standards making. Again, coming to this this particular issue, like this external pre-stressing and dry joints. This is a bridge which has been constructed with the external pre-stressing. Sadia in Assam. It's the longest river bridge in the country right now, actually speaking. And this bridge has the external pre-stressing with the precast segmental construction. And unfortunately, our design codes as well as the guidelines, Indian, does not encourage the use of the external pre-stress along with the precast segmental construction, which is if you're going for the epoxy glued segments with the internal pre-stressing, it is from the sustainability point of view or highly carbon intensive. It not only takes, say, for example, if it's a 10-kilometer bridge, it will take 1 more year because it requires the additional time for the application of the epoxy, and also when it is not an external pre-stressing, at the end of the use of this structure, say for example, this particular Sadia bridge in Assam is last for 100 years. If it is an externally pre-stressed bridge and along with the dry joints, it's possible to remanufacture the segment if it's lasting for so long and reuse it. From the circular economy point of view, also it's very useful, and also the inspection for the corrosion, whether it's taking place or not, can be done. So I think these are the sort of things I think in our code. This is just some of the examples how the code making also can help in really increasing the in achieving the carbon neutrality in our built environment. Now, another classical case, this particular bridge is coming to longest 24-kilometer bridge in India on the Mumbai Trans Harbour Bridge, as you can see here. Here, the role of the policymaker is very important. This bridge is going to be inaugurated very shortly. It's almost completed now. I don't understand, for a 24-kilometer bridge, why the single foundation, substructure as well as the foundation could not have been used for the multimodal transportation. That is, it's right now it's only for the highways, and why it could not have been made highways also in future railways and metros. I'm sure after some years now we'll be coming out with another 24-kilometer of bridges for the metros, basically. So I think there has to be a coordinated approach among the policymakers and the different departments when you are planning that from the carbon neutrality point of view. It's not that we are not done. You see here in Bogibel Bridge, Assam, we have got a multimodal transport system on the same foundation over here. Both highway transportation as well as the rail transportation takes place. The long span bridges in China, invariably they are going for this single substructure as well as a foundation concept for the multimodal transportation, as you can see here. Design efficiency, I think I suggest that the carbon value engineering, like similar to that of the value engineering, cost value engineering in our building as well as the superstructure during the design stage itself. You can see here, as I explained, A1 to A3 accounts for 50% of the carbon footprint, as you can see here, whereas in use stage accounts for almost 43% of the carbon footprint. I know right now, carbon footprint. If the carbon value engineering is done so that in use stage, by the increasing the durability and also by making sure that the resilient structures are taken care of, and also by using design efficiencies, it's possible for us to really reduce this carbon footprint in the first A1 to A3 and B1 to B5 modules. I think the carbon value engineering I propose to be done for this two modules over here. That's a product stage module and the in-use stage model for achieving the carbon neutrality in the coming years. There are other measures, design measures, as recycled materials, manufactured aggregates. It's all very well known. Recycling glass residue as a lightweight aggregate, replacement of OPC with mineral lead mixture, high strength, high performance concrete, self-compacting concrete, UHPC along with the high tensile steel, future upgradation and widening, durability and improved protection, and so all. And also designing for easy dismantling, reuse of components after end of the life, recyclable material, which can be flowed back into the construction later, and the circular economy can be achieved. That's very, very important. For the steel structure, very high strength steel, concrete to reduce mass, stainless weathering steel, fatigue for welded connections, standardization and modular construction, pre-stressing in steel bridges. I think that should be examined. Composite construction with the ultra high performance concrete, and of course, similar to that of concrete, design for future upgradation, connection details, better sustenance and durability, and corrosion protection. And again, the orthotropic floats also will reduce the critical mass in case of the steel structures, which should be adopted. This is the slide showing 90% of the carbon dioxide emission in the concrete is because of the cement, as you can see here. And you will have to use this mineral admixtures or the secondary cementitious material, as I explained you earlier. Unfortunately, all over the world, I think the slag as well as the ash has been extensively used now. It's been that the economic importance of this is realized. The cost of the concrete comes lesser when you use the fly ash as well as the slag, which is available as an industrial waste. That's why people are going for it, not because to achieve the carbon neutrality, but anyway, it's helping the carbon neutrality cause. Also, only 15% slag as well as the fly ash is available, balanced, as you can see here in this particular class. But very important to note, going forward, the future is calcined clay, LC3, what they call it, clinker, limestone, as well as the calcined clay cement. I think that is going to be the future, and it has to be extensive. It will be extensively explored. What I understand is it reduces the carbon footprint in the concrete itself by around 40% to 50% by using this LC3. Again, we have to explore the possibilities of using the FRP reinforcement bars, FRP pre-stressing strands, pre-stressing steel for both the purpose. The corrosion is a very big challenge all over the world. It's not, we are not able to find a solution to the corrosion yet. And there are some efforts made of using the stainless steel, aluminum reinforcement and coated steel bars. I think they are not very foolproof in the sense they're not helpful to that extent, in my opinion, and also it's been found all over the world. So I think the use of fiber reinforced plastics, whether it's a carbon, aramid or a basalt, I think we'll have to really look into. Now we have come out with a guideline in India. IRC has come out with a guideline for using in a limited way. But I think we'll have to come out with it has to be extended to the structures in general. That's what we'll have to do it. And also the FRP can be used as a pre-stressing strand. This is one of the cases where you can see here aramid FRP tendons in butterfly web panels has been used here. This is where the web panels, butterfly web panels being pre-stressed using the FRP tendons, as you can see here for a bridge in Japan known as Besonandi bridge, as you can see here. So I think it's one of the ways of really reducing the carbon footprint in the concrete itself. In new stage, I explained to you, I think in new stages all over the world, it's found 40 to 60%. Dr. Kyokosuga reports 60% in new stage carbon dioxide in Japan. I think in India also we have seen recently Ganga Bridge, Patna and Vasai Creek, Washi Creek Bridge has to be replaced. As soon as you replace the bridge within the life cycle or the service life, I think you are going to double the carbon dioxide emission to the environment during that period. That will have to. So that's very, very important. The durable design, durability design is important so that the curve comes like this, as you can see here at the bottom. Once you design for the durability, you should be having a minimum maintenance cost in the 100 years lifetime in case of the bridges. And also it should not corrode. I think the deterioration models should not set in, and the corrosion should not take place so that it becomes unserviceable during its lifetime. Similar to that of what happened in the Ganga Bridge at Patna. Within 20 years, that started giving troubles, and it was rehabilitated and repaired using the external pre-stressing technology quite a couple of times. And ultimately, the superstructure has to be replaced with, as you can see here, with the steel truss girders over here. This will, when it becomes unserviceable, you can see here the reconstruction costs the extra carbon dioxide emission to the environment, and whole your calculation of the whole cycle life during the design stage goes haywire. So I think it's very, very important during the design stage to design the structure as it should be durable for 100 years, and also the resilience also take in use of this, in case of this resilient structures also have to be designed for the climate emergencies in view of this climate change effects. Now, I'm just quoting, I'm very happy to quote Mr. Abhijit Kulkarni's paper here, in the recent Structural Engineering Digest. He came out with a very interesting paper. I really like that paper. I think he has, for the building sector, especially for the building structural systems, he has come out with some finding of him. I'm just using that. His finding was vapor slabs are more efficient RCC element for the slab, while PT slab is also comparable. M40 grade of concrete is most optimum. Higher grade of steel induces to the carbon dioxide emission, reduces the carbon dioxide emission. And the slag as well as the fly ash, he has quoted here slag. It's quite obvious even the other mineral admixture also can reduce the carbon dioxide emission. All these calculations has been done in the upfront carbon stage calculation stage. That is the cradle to completion boundary system stage. I think he has not done for the in-use stage for the buildings. Even for the buildings in use stage, I understand 40 to 43%. And also perhaps circular economy benefit is not taken over here. That is the reason for the steel structure is found to be highly carbon intensive here for the various projects which he has calculated for the various structural systems with the different material mix which he has here, he has conducted, as you can see here. And looking at his paper, my observation is that the foundation contributes only to the less than 10% in the building sector, unlike in our infrastructure sector where the carbon intensity in the foundation is quite large. So that is the difference between the building sector as well as the infrastructure bridges sector, basically. Structural systems like arch structural form can be examined because it gives the most of the structural elements are under the actual compression, actual loads. It's not subjected to the flexure, so it's not crack prone. When the structure is not crack prone, it's not corrosion prone too. So that I think it can be the in-use stage or the service life of the structure perhaps can be increased by going for the arch kind of structural form. Pre-stressing gives a lot of advantages, as you can see, both in the buildings as well as the bridges from the sustainability point of view. And the steel is another structural material which is highly, sustainability friendly, in my opinion. It's recyclable, durable, easy for maintenance and repair, serviceable, inspectability is high, reliability and redundancy is high, reduced waste and pollution. It's possible for us to go for the long span structure. Spanability, especially in case of the bridges, it is very helpful because the foundations are carbon intensive over there. Most importantly, the steel is recyclable and reusable to a large extent, 90 to 90% after the end of the life, and it gives a lot of credit in the carbon footprint calculation. So you can see here some of the long-lasting bridges in India is more than 100 years is steel bridges, but concrete bridges have not lasted so far. And also, if you really look at that, the steel is less accident prone compared to that of the pre-stressed concrete construction, especially the infrastructure. What I find is, though there are sporadical accidents in the steel structures also, but it's less accident friendly according to the statistics which I have. Again, I told you, because of the high strength to weight ratio as well as the ductility, I think the long-standing, the record-holding bridges in all categories, whether it's a suspension bridge, the cable stay bridge, or the cantilever bridge, or for that matter the arch bridge. Even normally the extradose bridge is not done using the steel structure, but using the steel structure, the extradose bridge has been made record holding bridge. It was the record for 312 meter. Even some of the hybrid bridges, like the hybrid of the suspension as well as the cable stay bridges, also are in steel. So that is because in the rivers, the wide and long rivers, where the foundations are carbon intensive, and it gives a lot of advantages. And also the recycling of the steel at the end of life is possible. So it becomes a highly the sustainability friendly product, the steel. Some of the outstanding aesthetically, it's a sort of a myth we have that the steel structures may not be very aesthetically pleasant structures, but on the other hand, if you really look at some of the bridges which has been undergoing on, it is constructed recently in India, highly aesthetically appealing bridges they are. And also there's a need, but unfortunately, it's even though it's a sporadic, the accidents are taking place in steel bridges as far as the steel structures during the construction. It's because there are not many trained or the experienced steel designers in the country. I think even the educational institutions also have a very less number of credits as far as the steel structure design is concerned. And also structural engineer also has to be taught fabrication technology as well as the steel material science, in my opinion, because unless this is taught, just designing the steel structures may not be helpful. So to make the steel more popular, perhaps the educational institution has a lot of role to play. I'm telling this because steel structure, in my opinion, is more sustainable structures from the carbon footprint point of view, achieving carbon neutrality point of view. The very high strength steel along with the ultra high performance concrete can be used, where the structural steel, even for the arches like this, and CFTs, like the concrete filled tubes as a composite sections can be used for spanning the structure or increasing the spannability of the structure, as you can see here, and as a sustainable option. This also can be done using steel. And there are instances where multi-story buildings using the composite steel columns are there. Again, here, if you use the steel alone, and if you don't take the circular economy advantage in calculating the carbon footprint, I think the steel structures, as I said, steel buildings may become unviable carbon footprint point of view. But if you take the circular economy advantage in the buildings, also the steel can become a viable option for achieving the carbon neutrality. High strength steel are also can be used to reduce the quantum of the steel itself in a structure. This is a classical example where, although in the Howrah Bridge at Calcutta, I understand by changing over from 350 grade of steel to the 450 grade of steel, almost 17,000 ton steel was saved. I think this is also high tensile steel, high strength steel has been used in both. So it's not that these are not used in the recent past. And coming to the stainless steel, the stainless steel from the maintenance as well as in-use stage reducing carbon point of view is very helpful. But only a disadvantage of the stainless steel is at the product stage. I think both, if you really look at it, I have given over here, the embodied energy is around 30 gigajoule, and the embodied carbon is around 2 ton for the ordinary steel, that's the average steel. Whereas for the stainless steel, embodied energy is almost around 60 gigajoule, whereas the embodied carbon is around 5. It's almost twice and thrice than the average steel. Unless the efforts are made to reduce the upfront carbon in the stainless steel itself, in terms of the embodied energy and the embodied carbon, I think stainless steel is not going to be a carbon friendly product, in my opinion. But the efforts have to be made in that direction because it's highly sustainable, in the sense it's highly durable in the service life in use stage. Weathering steel, another example. I think the weathering steel can last for 125 years, and I think we'll have to use this weathering steel so that in use state, the carbon it's almost around 40 to 50% can be reduced. The carbon dioxide equivalent to the environment can be reduced to a large extent. Incidentally, this weathering steel is the invention of India. As you can see here, the iron pillar of Delhi This is in Qutub complex of Delhi. This is the iron pillar. It's almost said to be 1600. Was fabricated by Vikramaditya, Chandragupta Vikramaditya II, the Hindu ruler. It was not fabricated there itself in Delhi. It was fabricated somewhere else, and it was brought by the Muslim rulers and installed as a trophy over here. And this has been lasting for 100,600 years, and it's a mystery. And at that particular point of time, some of the impurities like slag as well as the iron oxide were not completely removed in the steel, in this particular steel, and that is the reason for lasting. This reacted with the alternating drying and wetting environment and formed some sort of a film on top of that, and that film dust is protecting this particular iron pillar from corrosion for last 1600 years. So the similar concept has been used in the weathering steel all over India while producing it. In fact, it's the impurity which is not removed completely. It's ironical, has made this weathering steel possible. I think weathering steel could be one of the options really to reduce the in-use stage carbon dioxide environment. Another option is the modular accelerated construction, both in buildings as well as the bridges. It not only helps in accelerated construction, but also multi-cycle use of dismantled components by remanufacturing, which will bring down the carbon dioxide emission in A1 to A3 state. After the end of the life, it's easy for us to modular construction, easy for us to dismantle it, and after the end the stage also it will help. And also this modular segments can be used for remanufacturing after the end of the life stage also. So it will also help in the carbon dioxide, achieving carbon dioxide neutrality. Orthotypic plates can reduce, whether it's in pylon or...
Sorry,
Yes.
sorry to interject.
I'll
How
take
much time?
another 5 minutes. I'll finish it up.
Okay, okay.
Yeah. I'll finish it up. So I think orthotypic plate, I think all of us know, will reduce the critical mass of the structure itself by 30%. That will in turn reduce the load on the foundation. It's possible for us to achieve this carbon dioxide emission. And I will just skip some of the slides over here, and reducing the the embodied carbon at the product stage is very, very important. As I told you that all over the world in the cement production, it has been targeted to reduce this direct emission to the environment by improving the process and also the mineral ingredient formulation, changing the mineral ingredient formulation to a large extent. And even I have said that if it's possible to reduce it to 0.3 ton carbon dioxide equivalent for ton of cement production from the present 0.9 ton carbon dioxide equivalent, I think we'll be able to achieve a lot of carbon dioxide emission reduction in the environment. Similarly, in steel also, the world has targeted to bring it down from 2 ton carbon dioxide equivalent per ton steel of production to almost around 0.11 ton carbon dioxide equivalent. I think we also have to do work in that direction. So ultimately, what is not or what cannot be achieved by decarbonization of energy or the decarbonization of the fossil energy, and also other methods in new stage, whether it's like improving the durability, etc. The rest has to be achieved by a process called the carbon capture, utilization, and storage. What it is basically, carbon capture utilization is a process where carbon which is emitted during the, say for example, manufacturing of steel or even thermal power plants while producing the energy, even during the manufacturing of cement for that matter, is captured, it is transported, and some of the carbon which has been captured can be converted into some chemicals which can be used even in the construction industry for the circular economy purpose for curing, as you can see here. And it can be converted into the aggregates, carbon fiber, polymers, fuels like DME, SAF, and ethanol. Ethanol again is mixed with, all of you know that the petrol, and it can be used for reducing the fossil fuels, basically fossil fuels. So that's how it is used. What cannot be converted into this chemicals for the circular economy, I think it has to be sunk, or it has to be stored somewhere, and this storage has to be done almost around 2000 meter below, as you can see here. And in India also, the storage clusters have been identified. Almost around capacity of storage is around 600 billion ton, 600 gigaton capacity storage is available in India, all over India, as you can see in the slide on the different clusters. I think a lot of research is going on in the Indian institutions of technologies, as well as the Department of Science and Technology is taking a lot of interest in achieve, because it is not very easy to decarbonize the energy 100%. Basically, I think it has to be, I think it's expected 30 to 40% energy could be decarbonized by 2070. The rest has to be achieved by the CCUS. And the CCUS seems to be a feasible way of achieving the carbon neutrality in India, for which we'll have to work out. Now, I told you about the decarbonizing energy is a difficult task, and I'll just come to the conclusion, as I've already run out of the time, perhaps to a large extent. Decarbonization to carbon neutrality by 2017 built environment demands connected approach for all the stakeholders, as you can see here: owners, architects, designers, contractors, policymakers, suppliers, and manufacturers. Construction sector can contribute to carbon neutrality by 2070 built environment at the most by 10%. As you have seen here, most of the carbon dioxide emission is not because of the direct, not because of the construction process itself. Construction process accounts for around 4%, actually speaking. And it is because of the energy used, electricity used by turn, which is emitting the environment, emitting the carbon dioxide to the environment, and also the direct process of production of the construction materials like cement and steel. That is where the concentration has to be there. As a construction engineer, we can contribute by 10%, in my opinion. Thus, there is an urgent need for carbon minimum new technologies for decarbonization, steel and cement production, and also the CCU technologies going forward. With this, I stop here, I pause here, and I look forward to the very fruitful, like the panel discussions. Also, I would like to have a critical analysis and the critical view of my presentation, so as a feedback to me by our esteemed panelist, Mr. Abhijit Kulkarni. Thank you very much.
Thank you, Hegde Saab, for such a absorbing and excellent presentation. Only thing is, it took almost 2 hours, and I must profusely thank you. It was a very professorial kind of presentation, very well researched, and it covered the subject from cradle to grave. I mean, you started with definition of carbon neutrality, and ended with several case studies and your conclusions. I just felt as if I'm sitting in a institution, in a classroom. And I must mention also that during your lecture, you have received several bouquets and in the chat box, as well as in the Q&A box. Normally these kind of webinars, we extend till 2 hours. And since we have, we have almost exceeded that time limit, I don't think we should be able to take Q&A.
Yeah.
But let me first of all, introduce our esteemed panelist who is here, Mr. Abhijit Kulkarni, who is the project principal and country director of Bureau Happold in India. He has more than 28 years of experience in consulting civil and structural engineering field, and of which 18 years was in the Middle East. Till 2019 middle, he was in the UAE, heading the structural engineering team of a reputed European consulting firm. And he has been working on this subject of sustainability for quite long. So may I request Mr. Kulkarni to kindly share his thoughts based on the, and also critically give his comments on the lecture given by Mr. Hegde.
Yes.
Over to you, Kulkarni Saab.
Wow. Can you hear me well?
Yeah.
Amazing stuff, Mr. Hegde. Look, I started taking notes, but then I ran out of pages. So really well researched, well organized. Perhaps we should have a series of this, maybe.
Absolutely.
Because each of the slides that you have presented has a data which could be debated, discussed for 10-15 minutes for each of the slides. So it was that well, collated data. You started from all the way from the definition of carbon, CO2e, what it consists of. Then you started, I'm just taking the notes here. Then you started talking about, what is the circular economy and why we need to do it. Then you presented the way of, how to calculate it in terms of I-struct-T, ICE, the carbon factors, and then you give some equations there. And then you look at, how to optimize it, your years. That is fantastic. That is really, really well done. That's amazing. And then you talked about, some reduction methodologies. What I liked about the presentation is, your suggestion to cooperate and coordinate between the policymakers. That is, perhaps is the most required at the moment sort of action, because we will all technocrats. I mean, we will keep talking about this. We'll keep collecting data. We'll keep presenting it in various forums. But unless it is made mandatory, either by code or by policy, we all will be just talking about it.
Yes.
Right. So I think you made a very good point there, that it has to be coordinated amongst all the policyholders. And then if the Prime Minister has been, at the World Forum is committed to this, then we should have backup sort of how to achieve it, sort of roadmap clearly ready for it. And perhaps it might be under construction or under discussion, but it's not in a common forum. And then there's a way how you look at the infrastructure projects, and then there is a way how you look at the property sector projects.
Yes.
Infrastructure, you can influence, you can make it mandatory by authorities and put in government regulations. Property sector, even if you do that, there has to be some cash attached to it.
Yes.
Right now, all these property developers, they would definitely want to get early slab cycles, high cement content, because they can reduce the shutter faster and then get to the next level, and all the tall buildings. So there has to be some green finance options available. So if your option of QC SBS is fantastic. That if that is implemented in some form in both sectors, like infrastructure as well as property sector, it would help a lot. That if somebody is giving you a sustainable design, whether you can give them maybe some financial benefit, maybe extra FAR or whatever for property sector.
Yes. Yeah.
Right, and so that will sort of entice people to start looking into it. And then we talked about, we put in one of my slides, the study that we had done within Bureau Happold was more to do with single use of material. It was the structural steel was pretty high because the manufacturing was pretty high. If you look at the way structural steel is manufactured in India, it's more of a traditional method. But if you see that in UK, now they are refurbishing and re-rolling the steel, and very low embodied carbon factor for that steel. I mean, it's like 2.6 versus 0.6, something like that.
Oh, I see. Mhm.
So if we start using that, and India has enormous amount of structural steel already being used, which could be rerolled, repurposed, and then, fantastic. Then it will be much better in terms of reuse of materials. And you pitch one more point, which is, I keep talking to our guys within BH as well as with the client side. Design for dismantling. Right now, design for dismantling is, it's so important that if you want to really consider reuse of material, you need to think right from the beginning as to how you want to reuse it 50 years, 100 years down the line, right? And we perhaps need more framework for this. Perhaps the modular construction is one of that option that you could do. We are talking about some precast and post-tension precast frames, and which could be reused. You just remove the precast, you take them assembly down and reassemble. So there are various methods available. But again, we all are learning from various experiments done outside India and then rest of the world. But amazing presentation. I must congratulate you. I mean, you would have put enormous effort in pulling this together. Amazing. I mean, I'm flattened. Thank you very much.
Thank you.
Thank you.
I
Thank
see.
you.
Again, you have given me bouquet. I didn't want that. I said I want a feedback. Critical.
No, but
Where I could have improved.
no, it is. What I said is,
Yes.
perhaps what we could look at. I mean, maybe we should have had an initial discussion about how we are presenting it,
Yes.
and maybe we could have had maybe 2 or 3 sessions,
Yes.
which could have helped people, to sort of concentrate.
Correct. Yeah.
Your presentation is the course itself. one can probably do a 3-month course on embodied carbon and how to do. Really.
Very true. So I think basically, Mr. Hegde, this presentation has given me a thought that the next refresher course that IS Shakti is going to do would be probably on the subject of how to reduce the carbon footprint, and probably whatever material Mr. Hegde has presented, maybe it requires a little bit of elaboration on it to become a course by itself, as very rightly pointed out by Kulkarni. So I'm really sorry that I'm not in a position to take questions, but I have requested Mr. Vikas Verma to copy all these questions in the Q&A box and give it to Mr. Hegde.
Yeah.
And he will respond to all the questions, and I think it will be circulated to all the participants through email. So I think because we already, this is 7:15, 2 hours and 15 minutes. So if you all permit me, I would like to conclude. So in the conclusion, I would like to say that, such an extensive presentation by Mr. Hegde addresses the issue of carbon neutrality or the reduction of carbon footprint in the built habitat. This is, as in his concluding slide, he mentioned that this is only a part of the total problem. If we talk about, bringing in carbon neutrality by 2070, 90% comes from some other source. And therefore, as I mentioned in my opening remarks, that, it's not getting carbon neutrality by 2070 is a huge challenge, where individually or even collectively few of us cannot, it will not be possible for us to achieve unless the entire, machinery works towards this carbon neutrality. And I just want to share a little bit of information because this is a multiple intervention that is required. There is a agency which is called the Global State of Climate Action, done by Bezos. There is an agency called Bezos Earth. who with that agency is, trying to sort of assess globally the targets which were set in 2015 in Paris Agreement, how each country is faring in various fields. And I think it's very interesting for me to share this information. They have tracked something like 14 areas where, for example, power sector, agriculture, forestry, industry, building sector, and also the transportation sector, etc. And in these 14 areas, they have taken 37 indicators of progress. And the outcome in 2023 was that out of these 37 indicators, there is only one indicator on which the world is on track as per the targets set in 2015, and that indicator is the involvement of private sector companies to reduce carbon footprint. Other 9 indicators out of 37, which includes removal of fossil fuel subsidies, renewable energy, etc. They are off the track, but they are in the right direction. There are 21 of the indicators which are well off the track. In other words, they are pointing though in the same direction, but the rate at which the progress is taking place is rather too slow.
Yeah.
And there are 6 of these indicators which are actually moving in the wrong direction. So this is the state of affairs. And if we have to, ensure that by 2070, India achieves, though, as I think Mr. Hegde pointed out in his lecture, that India, in fact, is faring quite well in terms of, setting the target and fulfilling the target. So far, India's performance has been pretty good. But merely India's performance will not help us to achieve the target globally. After all, it is a global field. And therefore, all of us needs to put our effort. As far as the civil engineers and structural engineers are concerned, though our role may, be limited to 10%, as in the conclusion Mr. Hegde mentioned, but this 10% is also very, very important 10%.
Yeah.
And we are nowhere in terms of, we are only talking in forums like this, webinars, but in reality, we have a lot to sort of, achieve to get to the, working. And I'm really amazed the way Mr. Hegde has prepared himself to the subject, which is not in the practice. So I think a lot of lessons I have learned from Mr. Hegde as to how do we prepare ourselves for this, prepare for, this carbon neutrality. And I think our codes, our standards, our practice, our tender documents and our specifications needs a change, and the sooner the better. With this, I would like to conclude by once again thanking Mr. Hegde for his excellent presentation. Many of the participants have requested me to sort of get because they have not been able to digest also the presentation. So if you can give the handouts of the presentation, maybe it can be circulated to the participants. And I think we have also taken a video, YouTube, which the link can be given to all the participants so that if they want to visit and revisit the lecture, they should, because it's such an informative lecture. I'm sure most of us interested will revisit. And with this, and I also thank Mr. Kulkarni for being one of the panelists and giving his very informative and educative thoughts on the subject. And with this, I would like to conclude this particular session for this particular webinar.
Thank you. Thank you very much, Alok. Thank you, Alok.